We have a triple integral, and we're going to do it with cylindrical coordinates. Let's figure out what we're being asked to do here. We're integrating this function over the region defined by these statements here. And what do those statements actually give us? We have let's take a look. We've got here x squared plus y squared equals 1. That's a circle in the xy plane, which means it's a cylinder for us. So this is a cylinder. We have the we have a base of a cylinder going up. Above or below z equals 4, so the cylinder's cut off above at z equals 4. Z equals 4 is a plane. It's a horizontal plane. So that gives an upper cap to this cylinder. So we're below that, and above this thing here, well, what is this thing? That is a paraboloid. We know because the x and y are squared and have the same sign, and the z is not squared. And because the x and y are negative, it's a paraboloid that's opening downward. So we have, if I could extend maybe the x-axis backwards a bit, I can try to draw what we have. This paraboloid opening downward. And so you think of this as this portion is what we're integrating over. Think of that as a can or a cylinder with the bottom scooped out in a parabolic bowl shape. So there's a kind of a bump on the bottom, I guess. Now we could do this with rectangular coordinates. If we did this with rectangular coordinates, we would have double integral over some region R, and we would integrate in z first, and z is going from 1 minus x squared minus y squared on the bottom up to z equals 4 up above. And we're integrating the function square root of x squared plus y squared. We do that integral in z, and then we're left with the double integral. This is all from last time, section 16.4. We can do that integral. So I'm going to do this in rectangular coordinates, and I'm going to do it in cylindrical. I want to show you how similar these two things are and how we get the same answer either way. So we can do this integral in z, and we get z times the square root of x squared plus y squared, because this integral, as far as this integral is concerned, x squared and x and y are constants. We're integrating in z, so it's just the integral of a constant, which gives us z from 1 minus x squared minus y squared to 4, and then we have dA, and that's over some region R that we'll figure out later after we deal with z. So we've got our 4 times the square root of x squared plus y squared minus 1 minus x squared minus y squared times the square root of x squared plus y squared. And we're going to do a double integral of this. Now, to do a double integral, what do we need? To do a double integral, we have to know what's the region that we're integrating over in the xy plane. And we look at our original picture and look down at the xy plane. The shadow of that thing down on the xy plane is just the circle of radius 1. So this is x squared plus y squared equals 1. As a boundary, we have the inside of that thing to deal with. So if we want to do this double integral, it makes sense to use polar coordinates because the double integral is over a circle. So we use polar coordinates. This becomes the integral from 0 to 2 pi. It's all 360 degrees. Radius 0 to 1. And remember, x squared plus y squared is r squared. So this looks like 4r minus, what do we have? 1 minus r squared times r. And then there's the r dr d theta. And that's what we end up with. And if we do this as a triple integral in the way that we did in the last section. Now, this section's about cylindrical coordinates. So we're going to do this again, but in cylindrical coordinates. If we start right out of the gate with cylindrical, then the boundary we have, x squared plus y squared equals 1. That's just r equals 1. If we have z equals 4 in cylindrical coordinates. That's still z equals 4. And the paraboloid z equals 1 minus x squared minus y squared. That was the bottom of our region of integration. That looks like z equals 1 minus r squared. So those are the equations that describe our region of integration. And we can say z goes from 1 minus r squared down below up to 4 up above. The function we're integrating, remember, if we were integrating the square root of x squared plus y squared, in cylindrical coordinates, that's just r. So we're integrating r. We know from cylindrical coordinates we have an extra r, dz, dr, d theta. R goes from 0 to 1, and theta goes from 0 to 2 pi. And that's the triple integral that we deal with in cylindrical coordinates. Seems a little simpler. It's, it's the same as what we had before, but it might look a little easier to deal with or think about this way. We can do the z integral. This is r squared with respect to z. In the z integral, we're thinking of r as a constant, so that integral is just r squared z from 1 minus r squared up to 4. And then we'll have the dr d theta still. Integral from 0 to 2 pi, integral from 0 to 1. We plug in our values, and we have 4 r squared minus r squared times 1 minus r squared dr d d theta, and that is the integral, the double integral that we end up with. And looking up here, it's the same. It's the same as the double integral that we got using rectangular coordinates. So we'll stop at that point. We're just setting this up. We can do this double integral in r. It's the power rule on r, and then the 2 pi coming from the theta integral. But that's how we do it in cylindrical coordinates.